As Tom mentioned, I'm Christopher Kupitz from UWM. I used to work with Peter Froma from ASU, and I'm going to discuss a little bit today on the double focusing mixing jet for XFEL study of chemical kinetics. It's a paper by Dingji Wang from ASU, and in it we're going to start by first I'm going to talk a little bit about the BioXFEL setup, and then we're going to discuss some of the current injector choices, followed by a little bit of discussion of the time-resolved experiments, seeing as that's what this paper is really trying to get at, is some of the time-resolved, or the possibilities to make new time-resolved experiments at a BioXFEL. Then I'm going to discuss the actual mix and inject work done in the paper, followed by a little bit of conclusions and outlook. So I know that we've had several talks about BioXFEL and what's been done there in the past and the setup, so I'm trying not to take a ton of your time with repeating information that we've all heard already. So this was the original setup used by Henry Chapman. As you can see, you had a liquid injector that injected the sample into an interaction region with the LCLS X-ray pulses, which were then read out on CCDs. And from that, we collected the data. And up in the upper left-hand corner here, you can see an actual image of the jet jetting, and this plume here is actually the focusing gas as it's released into the vacuum. Oops, sorry. So here is the injector. And as you can see, everything looks very clean, and in the previous slide, everything looks very clean. But to give you an idea of some of the difficulties that are created when, or problems that are had when created this, those all look very clean. This is what it looks like at the actual LCLS. So this big, gigantic standing rod here, that's the injector setup on top of a lot of other equipment that we're trying to interface into this injector right here, and there's not a lot of room to work in, so this is what the injector people actually had to deal with at LCLS. However, on that note, the gas dynamic virtual nozzle, so termed GDVN, is very, very small. What you see here is the traditional GDVN, first, well, I don't know if first made by Dan DuPont, but first made for the LCLS, by Dan DuPont, Bruce Stoke, and Uwe Barstall. You see basically you have a capillary within a capillary. And what you have here is a smaller inner diameter liquid capillary that holds your sample, and then this outer capillary out here holds the focusing gas that will cause your stream here to really thin down. And in this image you can actually see as the stream thins down as it is focused coming out of the nozzle. And what this picture here on the bottom right is showing you is basically the effect of the focusing gas. The faster the flow rate to an extent, the smaller the droplets. So this top one on the bottom right, the top one is a lower flow rate focusing gas, and you can see you have bigger droplets. On the bottom one is a faster flow rate, and you can see the stream is thinner and you have smaller droplets. So here is maybe a little bit easier to visualize version. As I mentioned, you have the crystal suspension inside of the capillary, and then you have the helium or nitrogen gas causing a focusing effect till eventually it gets far enough away that the jet stream breaks up into a droplet region. And this is all happening under vacuum. So the second type of jet is called an electrospin jet. And what that is basically there is an electrode and you have to use some form of viscous solution, and the electrode basically causes the jet to extrude out a very, it's not a very thin jet, but a fairly thick jet into the chamber where you can then expose your crystals to it. And this sample, or this has the advantage of you're able to use larger crystals than you are with the GDVN, and I have a small comparison slide in a couple of slides that will show a few more of the differences. But this one is also another jet that's commonly used. It's commonly used. It was developed by Ray Sierra and Mike Bogan from Pulse.
Are you still connected?
Yeah, I am, as far as I can tell.
Okay, because we're not seeing. I mean, we're just stuck as far as we're concerned on the screen.
Can anybody else in here hear me?
Yeah.
Okay, never mind.
Microphone.
Okay, sorry. We're apparently having a small problem at UWM, so somebody came for a question. Sorry about the pause there.
Yeah, everything's okay here.
Okay. I don't know what's wrong then. Anyway, sorry. Continuing on with the talk. From the Electrospin, we also have a Viscous Jet, also developed by ASU. And for further notice, you can find Dan James' dissertation online. It's actually really easy to find. It was one of the first things that popped up. And he also gives a lot more detail and has a lot better explanation about a lot of the different jetting injectors that are out there for anybody who's looking for a source on this more. And what this injector is if you look at the left side picture, you can see two ball bearings right where the C is labeled. And what this is, basically, it's a pressure amplifier that allows you to push out very, very viscous substances like LCP. And so this is used for a lot of GPCR work, LCP work. Recently, I know Petra Froma's group has also developed an LCP mimetic that allows you to use both soluble and membrane proteins in an LCP-like environment without actually having to grow your crystals in LCP. And so this injector is huge because it allows for an extremely decreased sample consumption. And here, as I mentioned, the comparison between the two, on the left-hand side, we have a comparison of the LCP injector versus the GDVN. And on the right-hand side, we have a comparison of the Electrospin injector versus several other injectors, actually. And what you can see here is the sample consumption is vastly different. So in columns 1 and 2 of the left-hand side graph, you can see that we use a lot of protein, 10 milligrams, 15 milligrams, 10,000 microliters. That's a lot of protein for anybody to produce. So the LCP injector and the Electrospin injector, to a slightly lesser extent, use significantly less resources. We're talking microliters versus milliliters. So this was a vast improvement in injectors that can be used for solving structures. And the thing is, with time-resolved crystallography, you pretty much have to use the gas dynamic virtual nozzle because you have to be able to have a time-resolved study, which can be very difficult to do with a slow-moving jet like LCP or something similar. So what is time-resolved crystallography? It is the attempt to get structural and kinetic information from an X-ray experiment. Previous attempts at this have been, photosystem 2 and photoactive yellow protein are two that most of us are probably familiar with, so I'm sticking with those two because they're the ones that everybody's familiar with. And the way this has worked to date is you have a liquid stream that is injecting into the chamber with the interaction region, and then you have an illumination via a laser, whichever one will activate your protein, and you probe the sample stream sometime after the laser in order to determine what the illuminated state might be. And so in the past, this has worked. It worked on photosystem 2 to an extent. The resolution is relatively low, so really we're just we're saying, this is what the data is, but we can't be sure because the resolution is only to 5 angstroms. But on the other hand, with photoactive yellow protein, it worked very well, and we can see definite changes. And this proves to us that time-resolved crystallography is possible to high resolution at an XFEL source. Now, the problem with current time-resolved work is that it pretty much to date has solely relied on light-induced changes, which leaves whole classes of proteins that aren't capable of being probed using this. One of the most interesting sets of proteins, enzymes, that require a totally different method of activation, where you have some form of enzyme and a substrate that is maybe combined in multiple steps before you eventually have an enzyme and your final product. And a lot of people are very interested in what the conformational changes that enzymes go through. And an example of this, two examples. One would be this protein here. It's called CCNIR. It's a nitrogen reductase, and nobody really knows how it reduces the nitrogen. We barely even know where for sure the nitrogen is bound, but we do know that somehow or another it performs its goal. Another example of this would be a protein called beta-lactamase, which is a tuberculosis protein, and it basically cleaves the lactam ring of penicillins, which basically gives tuberculosis and antibiotic resistance. We know that's what it does, but nobody knows how it does that. And if we can figure out how it does that, we can actually possibly find a way around it so that penicillin would work on tuberculosis again. So this is a huge field that could potentially be opened up, but right now there was no way to do these experiments at an XFEL. So the first thing to figure out was the theory. And I will promise everybody I'm not going to go over all the mathematical equations. If you really want to go over that, you'd really be better off to talk to Dr. Schmidt, who published this paper. But the thing that I really want to point out here is at the bottom right-hand corner, you see the A, and that's a 1 by 2 by 3 micron crystal. Basically, the diffusion time into the crystal is 150 microseconds. And what he determined when writing that paper was that if you used a much smaller crystal, you might actually, the mixing times would be slower than the diffusion times, so it would actually be possible to get a significant portion of the crystal into the active state all at the same time. And so, to do this, a new injector had to be made. And this is where Dingji's paper came in. He was making that new injector. And it was actually an interesting idea based upon the current GDVN. And what they did is they added in basically a third capillary. Lost the word there for a second. And what this is the inner flow capillary, as it's labeled, will hold your crystals. The outer flow capillary will hold your substrate, whatever small molecule it is that you would like your protein to bind to see how it reacts. And as the inner flow comes out, the pressure from this outer flow, I should actually mention that the flow rate on the inner flow is very low, around 0.1 microliters per minute is what the paper quotes. And so that's very slow. The outer flow is significantly faster than that, and what that does is it has an effect of, right out of this inner flow capillary, it squeezes the protein jet down to about 1 micron, between 1 and 3 microns. And so what that does is it creates a very small diffusive layer so that the substrate gets into the protein crystal at a very rapid pace. And then all of that comes out and you have your traditional GDVN, which is gas focused, and that focuses the entire stream down to a small region, which increases your chances of hitting a crystal. On the bottom left here, you see an actual image of what the nozzle looks like, but I'm going to go to this nozzle because it's a significantly better image in my mind. You can see right here you have the inner capillary with the first layer of outer capillary and followed by the gas focusing capillary. And it's creating a jet where the two liquids basically mix right off the end of the first capillary. Now, to prove that this worked, they tested it using a fluorescent dye. And the top image here is the fluorescent dye mixed with water and then excited by a 528 nanometer laser. And so you can see, obviously, that the dye is fluorescent all the way throughout the stream. Now, on the bottom image here, what you have is the same dye is mixed with a quencher, which is then injected, and you can see that the mixing happens fairly rapidly and that the fluorescence is quenched only about 20 to 40 microns off of the nozzle. So that's showing that in their fluorescent time scale, in the one reported, the elapsed time was less than 1 millisecond. The fastest time scale that they report possible is 300 microseconds, which would make, if you remember the table shown up above, it would make the mixing actually more of a slower step than the diffusion into the crystal, which is what we want. And so they did a further simulation where basically the inner line flow was 0.1 microliters per minute. And these contours here basically represent how fast it mixes to a 70% concentration. And this calculation shows that the fastest time theoretically that you could get this to would be 150 microseconds, which would be basically, if you look back at that graph, it would be the same as the diffusion time between a crystal that is 1 by 2 by 3, which is, for LCLS, a fairly good-sized crystal. Now, there has been a little bit of other work done on this, but very little of it to date is reported. This is a microfluidic device paper that actually came out just before the Wong paper, where they built an injector out of a microfluidic device using soft lithography, and they did the same, basically the same fluorescent assays, but they didn't report a time scale as the Wong paper did. And so they also show that the mixing is more than capable to happen, but they don't say a time scale, so theirs is a little bit harder to judge. And also, to my knowledge, this type of injector has never been tested at an LCLS, so that also makes it a little bit harder to determine how accurate it could be when doing the actual experiments. So the conclusions and outlook is, because, as I mentioned, the inner flow is significantly slower than the outer flow, you have a high dilution factor, which, if you have a low crystal density, or really even with a normal crystal density, that could cause a massive diffusive effect for the crystals, which means your hit rate could be very low, but nobody's actually run the experiments yet. However, this paper does show that mix and inject is a viable technique for BioXFEL. I do know that recent beam times have been awarded to test injection techniques, but they were only about 3 weeks ago, so I don't believe any result has been published. And then I know at least one mix and inject beam time has been awarded, which will attempt to show that this technique is actually working. Does anybody have any questions?